We've talked about structural steel. Now let's look at another kind of material, structural concrete. And here is what we will be talking about. I've split this into two slideshows, and in this first slideshow we'll look at the actual materials, the cement, concrete, and rebar. And then in the second slideshow there's quite a bit of information for you, which we won't talk about aloud because there's a lot of information, but it talks about the types of building construction you run into: cast in place, precast, and tilt up, and then the way the slabs work structurally, and the name of the structural concrete code that you use. So in this slideshow we'll just look at the first two topics, beginning with what is concrete and what is cement. First of all, cement is not concrete. It's just one of the components of concrete. So when you hear people say, "I'm going to go pour some cement," that is actually not correct. They are going to go pour concrete. You can't pour cement, it just doesn't work. And what is in concrete is cement, that's one of the components, plus aggregate, sand and gravel, plus water. And I have a note at the bottom here. Aggregate is coarse particles of rock, and it includes sand and gravel. So when people say, "Oh no, concrete has more than just aggregate," they're thinking aggregate means gravel, but actually aggregate means all those particles. So anyway, concrete is cement, aggregate, and water. And the amount of water that's mixed into the mix has a big impact on the strength and on the workability. And you will see contractors do this thing called a slump test, which is a visual way of measuring how workable the thing is. And that's caused by how much or how little water is in it. But the big test is the strength test, the compressive test. And here's the deal. Concrete, after you pour it, begins to cure. And it cures for many days. And the longer it sits and cures, the stronger it gets. After 7 days, it's got some strength. After 28 days, that's where we consider that is its full strength that we've written into our specs. Now, I will just add, it's going to keep getting stronger as years go by, but 28 days is the mark at which we do our testing. So in our specs, we say we want concrete mix with such and such a compressive strength. At 28 days, and so when the concrete is poured, they pour these 6 by 12 inch cylinders, samples at the same time. And then at 28 days, when your pour has cured, your sample has cured also, and you send it to a testing lab where they compress it with a hydraulic press, and they measure how many pounds of force, how many thousand pounds of force does it take for the thing to blow up, basically, to fail. And that tells them what the compressive stress of this particular concrete mix is. What is this cement stuff? We call it Portland cement, and that's not because it's made in Portland. That's because when it was invented, this powdery stuff, back in 1824, the person who invented this cement thought, that looks an awful lot like this stone from a place in England called the Isle of Portland. It's an island and its name is Portland. There's a stone there, and this product here looks a lot like that. So I think I'll call it Portland cement, he said. But it's not actually made in Portland. And it's made by combining clay and powdered limestone and burning it very, very hot in a kiln. And after it's been burned, then it's ground to a fine powder. There is a problem with the cement industry, and that problem is carbon dioxide emissions. In fact, about 5% of the global carbon dioxide emissions that we are dealing with come directly from the cement industry. Some of those come from fossil fuels that are used to heat these furnaces, and some of them are caused by emissions from the burning of the clay and limestone itself. So this is a big problem that architects are working on addressing. What makes concrete get hard is that the cement, this powdered clay and limestone, has a chemical reaction when it's mixed with water, and that chemical reaction is called hydration. You notice that word hydro actually means water in Greek, and when we talk about we need to drink enough water, we say we want to be hydrated. So hydration is the chemical process that occurs when you mix this limestone stuff with water. And in this chemical reaction, it gets hard. And hydration continues for months and months, which is why concrete continues to get harder and harder as time goes by. When we make structural concrete, we are actually making a composite material, which means we're mixing two materials together. We are combining concrete and steel in the form of steel reinforcing bars. The concrete is strong in compression, the steel is strong in tension, and so together those two materials work to resist all kinds of loads that we might impose on them. And so we call this reinforced concrete. Well, concrete is very strong in compression, like this picture on the right. When you compress a thing, when you squeeze it, it's not strong in tension if you try to stretch a thing. So that's a disadvantage. Also, there is some cost involved. It's rather expensive because you have to build all this form work, the forms into which you pour the concrete. And then the labor that goes into making all that form work and pouring and removing and blah, blah, blah. So it's costly. And then it can develop cracks, which can be an issue. Advantages are, one advantage is its fire resistance. So steel has a problem with fire resistance. Steel loses strength when it gets hot, and this is a big problem in high-rise buildings. And we saw that in the Twin Towers when the steel columns buckled because of the heat. Concrete is much better with the heat of fire. So, and it doesn't need to be coated with fire-resistant coating because it's already fire-resistant. It's very strong in compression, and another cool thing about it is once you build the formwork, you could make it any shape. So let's look at that reinforcing. It's a reinforcing bar, and we call it rebar for short. And we put it in the place in the concrete that we think is going to be pulled on, that's going to feel tension. In a beam, that will be in the bottom of a beam. And here's the deal. Imagine that a beam is made out of a sponge. This is a demonstration of what a beam does. When you put a load on the beam, like the weight of a column, that beam bends a little bit, even though you might not see it with your eyes. And in the top it compresses, in the bottom it stretches out, it's in tension. And our problem with concrete is that it is weak in tension. So when you put a column on top of a concrete beam and it stretches on the bottom, it's going to crack down there. So we put steel rebar in the bottom, and it's the steel that is actually supporting that tension and keeping the thing from cracking. Rebar, I'm sure you've seen it in your travels around the world. It's this bumpy round steel bar. Here are some pictures of it. It comes in various kinds of bumpiness. And the purpose of that bumpiness is it helps the concrete, when it's liquid, when it's plastic actually, helps the concrete stick to the bar. The sizing of the bar is given in numbers, and those numbers represent the diameter of the bar in eighths of an inch. So a number 6 rebar, for example, is 6/8 of an inch. That's 3/4. 6 divided by 8 is 3/4. A number 4 rebar is 4/8. It's 1/2 an inch, and so on and so forth. And that's not exactly the diameter, it's the nominal diameter. Nominal means that's its name. Number 8 rebar is 8/8 in diameter, so it's 1 inch bar, and so forth. And by the way, rebar comes in different grades of strength. And the strength, you can look at a piece of rebar and know what grade it has by looking at the markings on it. When you look at a commercial project, before the concrete is poured, you will be amazed at how much rebar is in that thing. So we have bars that are running lengthwise of the floor slabs or the up and down the columns. And then we have bars that are perpendicular to those longitudinal ones, at right angles to them. And all those rebars are connected together by wire. I don't know if you can see in this picture, there are wire ties in there that hold those bars in place when the concrete gets poured. In columns, those vertical bars will be wrapped with these circular rebars wrapped in circles, basically. Those are called ties. And in a beam, you'll see rebars that go up and down in a box shape. Those are called stirrups. And then in the ends, they'll be formed with hooks. If you would like to read about the standards for rebar, here is your organization. CRSI is the Concrete Reinforcing Steel Institute, and that's where you will find all the specs and details. Oh, I should mention that if you live in Lane County, Oregon, the company that does rebar fabrication, a main company, is Far West Steel, and they have a separate shop that does nothing but rebar. They get drawings from engineers and architects, and they bend the rebar into secondary pieces and stirrups and hooks and all of that. And there are drafters who make drawings of those, but as you might imagine, it's a repetitive job. So that's the world of concrete, cement, and rebar.